Every single day, we use numbers without even thinking about them. Look around you. The digital clock tells us the time. Price tags tell us how much something costs. A speedometer shows how fast a vehicle is moving. And exam papers use numbers to show our marks. Whether we are reading a book, shopping, traveling, or studying, numbers are everywhere. These numbers all use the decimal number system, which is the number system humans use every day. Notice the digits shown at the top of the slide. There are only 10 different digits. They are 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Using just these 10 digits, we can represent any number, no matter how large. But have you ever wondered why the number 325 means exactly 325 and not 523? The answer is simple. The position of each digit gives it a different value. In this lesson, we'll discover how the decimal number system works and why understanding place value is the key to learning binary numbers in the next module. Let's look at the number 457. At first glance, it looks like 3 simple digits, but each digit has a different value because of its position. The digit 4 is in the hundreds place, so its value is 400. The digit 5 is in the tens place, so its value is 50. The digit 7 is in the ones place, so its value is simply 7. When we combine these values together, we get 400 plus 50 plus 7, which equals 457. Notice how the blocks in the picture get smaller from left to right. This reminds us that the value of each place decreases as we move to the right. The most important idea is this: a digit does not have a fixed value. Its value depends on where it is placed in the number. This concept is called place value, and it is one of the most important foundations for understanding both the decimal and binary number systems. Now let's explore how place values are organized in the decimal number system. Each step you move to the left represents a power of 10. We begin with the ones place. The ones place has a value of 10 to the power of 0, which equals 1. Next comes the tens place. This is 10 to the power of 1, which equals 10. Moving one step higher, we reach the hundreds place. This is 10 to the power of 2, giving us 100. Finally, we have the thousands place. This is 10 to the power of 3, which equals 1000. Notice how each level in the staircase is larger than the one below it. Every time we move one place to the left, the value becomes 10 times greater. This predictable pattern is what makes the decimal number system so powerful and easy to use. Understanding these powers of 10 will also make it much easier to learn the binary number system, where the same idea is used, but with powers of 2 instead of powers of 10. Let's see how positional notation works, using the number 325. Although the number contains only 3 digits, each digit has a different value because of its position. The digit 3 is in the hundreds place, so it represents 3 times 10 to the power of 2, which equals 300. The digit 2 is in the tens place, so it represents 2 times 10 to the power of 1, which equals 20. The digit 5 is in the ones place, so it represents 5 times 10 to the power of 0, which equals 5. When we add these values together, we get 300 plus 20 plus 5, which equals 325. This is called expanded form, because we break the number into the value of each digit. This example clearly shows that a digit's value is determined not only by the digit itself, but also by its position in the number. This principle is known as positional notation, and it is the foundation of both the decimal and binary number systems. Now that we understand the decimal number system, let's take a quick look at the binary number system. On the left is decimal, also known as base 10. Decimal uses 10 different digits, from 0 to 9. Its place values are based on powers of 10, such as 10 to the power of 0, 10 to the power of 1, and 10 to the power of 2. On the right is binary, also known as base 2. Binary uses only 2 digits, 0 and 1. Instead of powers of 10, binary uses powers of 2, such as 2 to the power of 0, 2 to the power of 1, and 2 to the power of 2. Although the base is different, the fundamental idea is exactly the same. The position of each digit determines its value. So whether we are working with decimal or binary, we always read numbers using place values. In the next lesson, we'll explore the binary number system in detail and discover how computers use only zeros and ones to represent all types of information.